Bismillahirrahmanirrahim. Today we will start our second lecture on thermodynamics. The topic under study is heat capacity. The definition of the heat capacity is the amount of heat required to raise the temperature of a system by 1 degree. 1 degree means by Kelvin or by Celsius scale. Required means absorbed. It means how much heat is absorbed if the temperature of the system rises only for 1 degree change. It is represented by C, and C is we have written the C in small letter. It means it is a path function. C is mathematically we can define it that C is equal to Q by M into T2 minus T1. It means the amount of heat required for a given mass M for the change when the temperature will change from T1 to T2. T2 is the final temperature and T1 is the initial temperature. When we will take the 1 mole of the substance, then C will become C is equal to Q divided by T2 minus T1. We will subtract T1 from T2, so C is equal to Q divided by del T. As I have told you that del indicates change in, so change in temperature, del T is equal to change in temperature. Heat capacity varies with temperature. For infinitely small change means for very small change we will write instead of del we will write small t d. So C is equal to dq by dt. This heat capacity can be expressed in two ways. First is the specific heat capacity. Second one is the molar heat capacity. The amount of heat absorbed by 1 gram of substance to raise the temperature by 1 degree. 1 degree means you can say that temperature can be taken in measured in Kelvin or Celsius scale. Molar heat capacity, it is the amount of heat absorbed by 1 mole of substance to raise the temperature by 1 degree. The difference between specific heat capacity and the molar heat capacity is the amount of mass taken. If you take the mass in 1 gram, it is known as the specific heat capacity, and if you measure the mass in 1 mole, then it is known as the molar heat capacity. The units of the molar heat capacity are joule per Kelvin per mole. Joule per Kelvin per mole. Next is the thermodynamic treatment of heat capacity. Heat capacity can be measured at two different parameters: heat capacity at constant volume, heat capacity at constant pressure. Because it gives different values of the temperature change at constant volume and at constant pressure, therefore we will measure at constant volume and at constant pressure separately. First we will study the heat capacity at constant volume. Heat capacity at constant volume is indicated by C. As a subscript you will write V. This small v indicates the constant volume. Mathematically you can write it in this form: Cv is equal to Qv by dt. It means heat absorbed at constant volume with respect to temperature. According to first law of thermodynamics, dE is equal to Q minus W. dE indicates the change in internal energy. This is equal to heat absorbed minus W work done. As we know that the work done in thermodynamics is the pressure volume work. So for the pressure volume work, W is always equal to P dV. We will substitute the value of P dV at the place of W. dE is equal to Q minus P dV. At constant volume, dV is equal to 0. It means no change in volume will take place. V2 minus V1 will be equal to 0. So dV is equal to 0. Write 0 in place of dV. So when you multiply 0 with P, answer is always 0. So dE is equal to Q. At constant volume, we will write V as a superscript, as a subscript. dE is equal to QV. Put the value of QV in equation first. QV is equal to dE, so write dE instead of QV. So CV will become CV is equal to dE by dt. We concluded in this form that heat capacity at constant volume is the rate of change of internal energy with respect to temperature. Rate of change of internal energy with respect to temperature at constant volume. dE will change into partial. It is known as the partial differentiation. This sign is called partial sign. D will change to partial sign as this change is for the infinitely small change. So for infinitely small change we write partial. For small change we write D, and for infinitely small change we write partial. CV is equal to partial E by partial T at constant volume. Next we come to the past heat capacity at constant pressure, Cp. Mathematically it can be written as Cp is equal to Qp by dt. According to first law of thermodynamics, dE is equal to Q minus W. As we know, W is the pressure volume work, so W is equal to PdV. Write PdV at the place of W. dE is equal to Q minus PdV. Q can be equal to, Q is equal to dE plus PdV. At constant pressure, Q is written as Q and subscript as a subscript write P. Qp is equal to dE plus PdV. Put the value of Qp in equation first at this point. So Cp will become Cp is equal to dE plus PdV divided by dt. We can write it in this form also. Cp is equal to dE by dt plus PdV by dt. In terms of partial differentiation, it can be written as Cp is equal to partial E by partial T at constant pressure plus P into partial V by partial T at constant pressure. We will bring P outside this bracket because it is constant. Enthalpy in mathematical form is written as H, as we know, H is equal to E plus PV. Partially differentiate above this equation with respect to temperature at constant pressure. Dear students, always write this statement in this form. Partially differentiate above equation with respect to temperature at constant pressure. So we will write partial is, we will say that we will partially differentiate this equation. Partial H by partial T at constant pressure is equal to partial E by partial T at constant pressure plus P into partial V by partial T at constant pressure. Again I will tell you that we will put P outside this bracket as it is constant. Comparing equation 2 and 3. This 2 and 3, we will write that Cp is equal to partial H by partial T at constant pressure. At these two sides are equal, they will cancel with one another, these two sides. So Cp will become equal to partial H by partial T at constant pressure. Like Cv, we will define this Cp that at constant pressure, rate of change of enthalpy with respect to temperature is heat capacity at constant pressure, this one. These are all about the Cp and Cv. Our next topic is prove Cp minus Cv is equal to R. So we will derive the result thermodynamically. When a substance is 1 mole and for infinitely small change in temperature, heat capacity at constant volume, as we know, Cv is equal to partial E by partial T at constant volume. Heat capacity at constant pressure, Cp, is equal to partial H by partial T at constant pressure. Partial H indicates change in enthalpy and partial E indicates change in internal energy. The difference between two capacities means heat capacities, is represented as Cp minus Cv is equal to, put the values, partial H by partial T at constant pressure minus partial E by partial T at constant volume. Write it equation as number 1. As we know, H is equal to E plus PV. So, partially differentiate this equation. We know it. How to differentiate it? Partial H by WRT. This indicates with respect to. Partially differentiate with respect to temperature at constant pressure. So, partial H by partial T at constant pressure is equal to partial E by partial T at constant pressure plus P partial V by partial T at constant pressure. Substitute or put the value of partial H by partial T here at this point in equation number 1. Cp minus Cv is equal to partial E by partial T at constant pressure plus P into partial V by partial T at constant pressure minus this one, partial E by partial T at constant volume. It will be equation number 2. Next, the internal energy E of a substance is the function of temperature T and volume V. So, differentiate this equation partial E. We will differentiate this equation partial E with respect to T at constant volume and partial E with respect to V at constant temperature. So, partial E is equal to partial E by partial T at constant volume into dt plus partial E by partial V at constant temperature with respect to dV. Dividing both sides of it, this is the equation number 3. Dividing both sides of equation 3 by dt at constant pressure, this equation will become partial E by partial T at constant pressure. This is equal to partial E by partial T at constant volume. Divide this equation as I written by dt. So dt by dt plus partial E by partial V at constant temperature into partial V by partial T at constant pressure. Partial E by partial T at constant pressure is equal to partial E by partial T into V plus partial E by partial V at constant temperature into partial V by partial T at constant pressure. Put the value of partial E by partial T at constant pressure in equation number 2. Cp minus Cv is equal to partial E by partial T at constant volume plus partial E by partial V, this one at constant temperature, partial V by partial T at constant pressure. These both are the multiples of one another. Note it. Plus P into partial V by partial T at constant pressure minus partial E by partial T at constant volume. Cancel these two. Partial E by partial T at constant volume. Look at this, that both are same, equally same. Partial E by partial T at constant volume. This is minus partial E by partial T at constant volume. So they can be cancelled with one another. Cp minus Cv is equal to partial E by partial V at constant temperature into partial V by partial T at constant pressure plus P into partial V by partial T at constant pressure. Look at this. You can bring these constant outside the bracket. So partial V by partial T at constant pressure, partial V by partial T at constant pressure, bring this value at outside the bracket. So partial V by partial T at constant pressure is outside the bracket. The remaining value will be partial E by partial V at constant temperature plus this P1. This is the equation number 5. Now, for an ideal gas, partial E by partial V at constant temperature is always equal to 0. Note that we are always considering the ideal gas. Hence, above equation 5 is written as Cp minus Cv is equal to, as this is 0, 0 plus P into partial V by partial T at constant pressure. Cp minus Cv is equal to P into partial V by partial T at constant pressure. This is equation number 6. For 1 mole of ideal gas equation, as we know, PV is equal to nRT. Quantity is 1 mole, so N is equal to 1 mole. The remaining value will be R is equal to, here, bring the R here, R is equal to PV by T. Now differentiate this equation 7, this one, with respect to temperature at constant pressure. R is a constant, we can't differentiate it. R is equal to P, this is constant, so we can't differentiate it. We can differentiate only partial V by partial T at constant pressure. Now look at the equation number 6 and equation number 8. This value and this value, these are the same values. They will be cancelled one another when we will compare the equation 6 with equation 8. This is the equation 6, this is the equation 8. These two values are same. They will be cancelled with one another, and the remaining result will be Cp minus Cv is equal to R. Hence proved. So this is all about the today's lecture. Thank you.